Welcome to week 4, where we start to look at electrical power. Last lesson we were looking at circuits and how to analyse them. We saw how to use Ohm's law and Kirchhoff's laws to calculate quantities in circuits. This lesson will continue looking at circuits, but now we're going to also look at power and energy. We'll then have a look at AC rather than just the DC circuits we've looked at so far. And if there's time, we might start on our next big topic, which is magnetism. Now, our reason for having electrical circuits is so that we can pipe electrical energy into our homes and businesses and convert it into the forms we need with resistors. But the next question is, how much energy does a resistor convert? It depends on two things: how long it runs for, but also its rate of converting energy. So, for example, I run each of the appliances shown for 1 hour. How much electrical energy have I used? You can see that the LED, the light-emitting diode, light bulb uses the least. That's why many people are using them rather than the regular light bulbs now. Then we have the laptop at 216 kilojoules, the fan at 360, but obviously the biggest user of energy by far is the air conditioning unit. So we introduce a quantity called power with capital P. It is the rate of using energy. Since we're only looking at cases of constant rates of power, then we can say that power is just energy over time. Now, to derive an equation for power in terms of other circuit quantities, consider a potential difference V across a resistor, that device from A to B there, that has a current I flowing through it. That means an amount of charge, delta Q, is passing through that block, the electrical device, per second. The electrical potential energy lost by that charge is U equals delta Q times V. So power, which is energy over time, is delta Q over T times V, which is just current I times V. So we have our equation, power equals current times voltage. That means watts is equivalent to amps times volts. Now, since power equals energy over time, that also means that watts is the same thing as joules per second. So let's do a calculation. We have a torch here with 2 AA batteries, each 1.5 volts. So we have a voltage of 3.0 volts, and the current through that light globe is 0.4 amps. Firstly, we'll work out the power delivered to the bulb, and then we'll look at the energy dissipated in that light globe when it's been running for 5 minutes.